now for a dissertation. First lecture 30 minutes, and I would like you to start now.
Okay, thank you. Thank you very much. So, thank you very much, professors. Greeting. Since we have a quite diverse topic covered in this dissertation, I'll try to make the presentation more accessible towards a broader range of interests. So before we start, I'd like to take the chance to express my gratitude to my supervisor, Professor Philip. Thank you very much for all the support through the Ph.D. journey. And also I truly thank all the committee's members for this dissertation. Professor Philip Geyer, Professor Matthew Sandar, thank you for all your comments. Professor Michael Becker, Professor Johann Hack, thank you for joining online. And also Professor Kantja Benfer for being here. So my dissertation title is Beyond Predictions, Alignment Between Prior Knowledge and Machine Learning for Human-Centric Augmented Intelligence. And I actually chose this topic at the quite early beginning of my PhD journey when I joined a research project focused on developing a machine assistance for designers, which really made me start thinking about what this term truly means, especially in domains like building engineering and design, where the assistance is not just about, providing the numerical outcomes or the simulations. It actually involves supporting some of the very core of our human capabilities, such as interactive problem solving, conceptualization, reasoning, and the ability to develop based on our experience, knowledge, or even intuition. So to start with, I'd like to take a quick glance in 1985. In this year, an American professor, Donna Haraway, wrote, "By the latest 20th century, we are cyborgs. Both imagination and material reality will construct any possibility of historical transformation." In this year, a lot of digital products start emerging, but they still look really primitive back then. Most of them are made by pixels and handcraft rules. However, in merely less than 40 years, the technology can already enable us to generate videos with simple text inputs and even also help us to do the conceptual designing at the expert level. In the research and engineering, the newest large language model can already help us to understand complex problems that only few people in this world can fully comprehend it, or to propose a really solid improvement for chemical reactions. Let's say a task used to took a scientist, an entire team, a whole year to validate. So we already see this revolutionary achievements of digitalization and AI. We couldn't oversee its potential impact in the future, which reminds me another visionary English writer, the Herbert George Wells, wrote in 1920. He says, "The civilization and human history is a race between education and catastrophe." Maybe through the historical span, we are like in here, and maybe our near future might look like this. So this idea really shocked me and becomes the fundamental driven of me thinking and writing this dissertation. So before we dive into the main chapters, we shall see what AI is different than us. Machine learning is a data-driven process. It carries advantage to scale up and can surpass interpretability to capture the implicit patterns behind the data. On the other hand, we humans also got quite decent abilities. We can do abstract modeling, we can do few shots learning, we can do analogy and reasoning, and such abilities are not quite data-driven applicable, at least not for now. However, at this point, the trust issue often arises. We feel even threatened, especially when AI reaches or even our performance in some tasks we used to dominate. But the twist is, why shall we view AI as our opponent when it has the potential to be a powerful assistant? It's not about choosing between AI or our human cognition, but it's about doing works in combining these two strengths together. And that points out my major effort in this dissertation to make the alignment. I try to make my effort to bridge the gap between the human and the machine intelligence so that it can enhance our human capabilities, specifically in design, engineering, and scientific discovery process. So to approach this, this dissertation is organized into 3 sections. In each section, I'll try to address one key question of the topic. The first one would be the decision-making process alignment. I try to answer the question, how do we design a framework to incorporate with our dynamic decision-making process to see if it works? And the second, we move to the methodological alignment. I try to fully utilize the available information from our prior knowledge and embed it into a data-driven method to minimize the performance gap, to enhance the model applicability and the user trustfulness. And finally, it's about the communication efficiency. I try to answer the question, how do we incorporate and improve the user-computer interaction patterns? That would be the 3 different sections. So the journey begins. For the first part, I like to start with a question. It's the car part of our body when we drive? The answer is yes. In a cybernetic concept, human and the car will become a construct when we drive. It can help us to reach longer distance in a shorter time and in a safer manner. And to achieve this, the ergonomics, or what we call the human factor engineering, it's really important. Analogically, when we try to design the machine assistants to help us make informed decisions, it's also important to investigate such factors to compile with our decision-making process. So we can call it human factor engineering in a cognitive way. So let's take a glance of our decision-making process. We might hear about the story about this golden touch, King Midas, as he decided to get the reward of things he touched become gold. But at the end, he realized that he couldn't eat or hold his daughter because they would all become gold. And that turns out a really tragic story. So from this story, we can see that actually our objective might not be fully comprehensive or even barely express what we truly want. So our decision-making process could be uncertain, it's dynamic, and it's quite iterative because we couldn't foresee all possible conditions in the future before we got the abilities or got the assistance. However, our current machine learning model is typically deterministic. It normally contains a single preset objective with a fixed input data structure, and the whole process is an end-to-end black box behavior. So if we ask an AI to run our preset objective based on this logic, no matter how detailed we set, it's highly possible it will lead to something bad or something unexpected. The reason is that in reality, our objective is not static. We adapt or refine it as the new information arises. So we can see there's a huge misalignment in here. So in order to design the machine assistants, it becomes quite clear that we should make AI to accept dynamic inputs involving our human feedbacks, and it should also generate outputs under uncertain conditions. And in order to make us to understand the process and to make a proper inference, the model should carry its interpretation methods. And then such incremental updating strategy could avoid the pitfalls we mentioned before, which would bridge the gap between the machine outputs and our human value through the process. So to make such machine assistants, I got the organizational inspiration by our human nervous system, which start with a single agent to deal with the uncertainty identification and different prediction mechanisms. And then different agents communicate with information and uncertainty aggregation to, at the end, achieve a system level of evaluating multi-objectives with interactions. So at the system level, we can then apply the multi-objective optimization to the machine assistance framework to allow it to provide the optimal front. For the application, I put such assistance in the context of the sustainable building design recommendation regarding the building energy performance, environmental impact, and also the operational costs. So once we put all these things together, we have this demo. So as you can see that with the dynamic different inputs, it will generate output with uncertainty simultaneously. And in here you can choose different types of building, and you can also select different levels of details, and the whole system can accept this incomplete data inputs and still give a proper estimation of corresponding indicators with this uncertainty range. And because we already embed with interpretation methods, so you can see that why this combination of input features results in these outcomes, and also it can help us to make inference. In here, you can see that the potential impacts of selecting different windows will affect the results. So here is the optimal front of the optimization algorithms, and I run the clustering algorithm to cluster some similar patterns. In here, it will be different design patterns, and such information you can already feedback to our designers or engineers so that they can make further decisions. So I know that in here the design pattern is not really intuitive, so I'll show in this page. So based on set configurations, so the machine assistants can actually give a really promising design patterns that fits for our sustainability objective, and they can be really good validated by our domain experts and engineers, which I personally really impressed because I don't have such domain knowledge in my mind, but actually by interact with this machine assistants, it can make me achieve such solutions. So that it's part one so far. For the second part, I like to start with also a question. Imagine you've been tasked to explain what is an elephant to an alien. How would you approach this? One promising method is to use the deconstruction approach. We describe the elephant by its part. The long tusks, the hard skin, the massive ears, etc. So it's a mindset to break a big thing into smaller and understandable pieces, which is more similar to our knowledge-based simulation. We use our formula, we use our logic to construct a system and then to describe it. On the other hand, instead of detailed analysis of each part, we can look the elephant as a complete entity. We observe its behavior, the way it interacts with the environment, and how it moves. This method is more similar to our black box data-driven methods we often use. The emphasis is on overall experience rather than explainable details. But does one necessarily better than others to describe an elephant? The answer is no. There is no one best way to formalize information for describing a problem. We always use all available information from our knowledge to our data, and we usually approach both ways together. And that brings the key question of this section. How can we integrate both approaches together in our domain? So to answer this question, I organized a systematic integration regime in a 3-level structure. I called it the ladder of knowledge integration. With the ascending integration level, the model actually gets new abilities. So start from the bottom. As you can see, there's two small moments. One represents for the machine learning methods. Another one would be our simulations. And you can see these two small moments are holding hands together. That means they share the information via the data. At this level, we try to integrate our prior knowledge to process or to enrich the data. Move to the second level. As you can see, these two small men already merged to a bigger man. That means it's a combined approach. It actually means that we use our knowledge to modify the modeling process so that this bigger man can achieve the ability that small men cannot do. So move to the third level. As you can see, this bigger man can wear a hat, holding a sword, and have an idea. That means it's generating new knowledge. So at this level, we try to use our knowledge to make model discover knowledge directly from the data. So I will start the case from the bottom. So at this level, level 1, the knowledge we mostly use is direct modeling knowledge to process or to enrich the data so that we can enhance the model's performance within the given data range or its interpolative performance. And we have examples, previous study as an example to demonstrate this concept. As we try to predict one building performance or building load, we can always use our domain knowledge to decompose the behavior into a linear part and nonlinear patterns. And then we can use our simulation to reconstruct the linear part and then use the machine learning to capture the hidden factors behind the nonlinear patterns. And we prove that it's a quite general applicable approach for better predictive modeling. not only we can pre-process the data and modeling them differently, we can also use our domain knowledge to generate data for machine learning model, and we call it the hybrid framework. And we proved that even a really basic simulation input can already largely improve the final predictions accuracy compared to a pure machine learning model because of the data augmentation. Not only the machine learning can learn the information from historical behavior, we can also embed our prior knowledge and the building information into simulations and feed in as the data. So as you can see, it would achieve the quite advanced performance, and it will ease our modeling efforts. So that's level 1. Move to the second level, the combined approach. The knowledge in here is more referred to extracting some general patterns from specific case, or what we call the inductive logic, to modify the whole modeling process so that we can enable the model to conduct more extrapolative or more flexible prediction in new cases. So one example would be our previous studies. We use the component-based machine learning to simulate different building performance. It means that we decompose the building by its zones and components, and then we train each one as a specific machine learning model, and then we can recompose it to predict new buildings, just like we play Lego blocks. And the results, it supports that this framework can really well predict the performance in different shapes of a building, even if it is not in the training set. And the reason is that because when we decompose the building into subsystems, so when we predict the new buildings, it actually turns the extrapolation problem of the building level into the interpolation of the component level. Just like I said, different buildings are made of same basic Lego blocks. So this framework can carry several advantages. First, it's really robust against the sparse and noise data inputs, and it would really efficient to use the data from different entities. For example, we can use the window data of this building and wall data from that building and combine together, and we can predict new buildings. And because of this framework, you can also accept incomplete input data with higher interpretability because you can trace back to the component level. And all these characteristics adds up together, it will become, it would certainly reduce a lot of modeling effort and deployment cost in the real world industry. Because we extract these compositionality information from the system to put it into the model organization to provide these extra flexibilities. Another case I want to mention at this level is about modifying the modeling process in a scenario of the building system control. There is an advanced approach in machine learning called reinforcement learning. They actually train a machine learning model or an agent to interact with a programmed virtual environment to get certain optimal behavior. The outcome is more or less like this. However, to code such virtual environment for our domain is quite difficult. It's not really engineer-friendly or applicable. So I try to open this black box and embed the system simulation into the environmental setting. In a nutshell, a simulation and a predictive machine learning model would create a dynamic rolling window environment, and we can train another machine learning model to interact with this simulation and to get the optimal control signals. And we conclusively prove that it achieves better performance than rule-based control and model predictive control. And what's more, we can even replace the simulation with the component-based machine learning we mentioned before, and it will allow the agent to run the optimal behaviors in different energy systems and settings, and it will generate a really powerful agent for this control. For the third level, as we try to apply some general rules into specific cases to discover knowledge directly from the data, or what we call the deductive logic, it is the key to make the machine learning to avoid the potential bias, the knowledge input by our personal limitation. How do we achieve that? So there's a really common question we usually ask in our domains, what if questions. And this question actually means a series of actions to determine the most compatible adjustment with a set objectives. And this action and process is actually the core of our decision-making support. And during this process, The causality is really important. I would show with one case. In this picture, you can see there's two factors. One is ice cream sales, another one is shark attacks. Across the time, you can see both factors are highly correlated to each other. So if you ask somebody who doesn't have any common sense or ask a machine learning model, it will tell you maybe, oh, we should reduce the ice cream sales to avoid people die from shark attack. And obviously that is wrong. What happens actually in our mind is we kind of construct a skeleton that we can see that the hot summer season is actually the common cause of both factors, and that makes these two factors have this fake correlation. So actually the knowledge we try to bring it into the machine learning, it's not about ice cream or sharks. It's about this asymmetrical association between the factors. That means if we change the cause, the effect will change. But if we change the effect, this condition is not be occurs. So we can get the proper conclusion. The hot summer season is it's a compound of both factors. It's not about ice cream. So once we clarify this situation, then we can, I introduce the whole causal inference into the building engineering domain, which the model can learn from the data how change one factors could potentially impact others. We call it the causal skeleton. And this skeleton is more like our knowledge. It can be reused into a new case and can be expanded into new cases. So in this case, based on this skeleton, it can tell you, for example, if you want to properly see how change the building window area will affect the heating load, it tells you that, oh, if you want to do that, then you should control the wall-to-window ratio, the ground floor area, number of floors, and also the floor heights, so that you can get the proper estimation of these two effects. And this provides a foundation for model to answer what-if questions correctly, and provides a data-driven approach to generate information that can be cross-validated by our domain knowledge or to use to avoid our knowledge biases. So that is the level 3 cases I mentioned in here. So here's the short summary of this section. As the session comes to the end, I found that, interestingly, there's a really well-known theory called the Piaget's stage. It's about how does our human cognition developed during the childhood, which this stage aligns perfectly with our the ladder of order, which provides a really good, solid support from a cognitive science perspective. So that's part 2. Finally, it's the part 3. It's about interaction patterns. In this part, I try to make my effort to challenge one old question. Does the limit of my language mean the limit of my world? So I try to investigate in two major important directions. First will be how we can reinforce the information utility between the human and the AI. And the second is how we can expand our communication bandwidth between the AI, our works, and our mind. For the first direction, I extend the causal model example from the last chapter and more focus on the interaction patterns. So in the engineering domain or scenarios, we might observe something funny. For example, why in my case, the higher isolation standards leads to a lower energy efficiency? And then the causal model can check the data, generate this skeleton, and gives you a reasoning conclusion and, hey, you should consider about the building construction area to avoid a biased result. And based on this extra information, we can properly run the simulation or the data-driven modeling to feedback with the proper outcomes, and you can see, oh yeah, that's right, awesome, and then I will do something further. So you can see that this data-driven model, especially at level 3, can be an information assistance to extend our cognition and overcome our biased prior knowledge. And you can see that actually in this case, the information is being processed through different entities with mutual reliance. All these elements combined together will become a much more stronger cognitive construct. So I try to summarize this information flow into a symbolic relationship among different entities, so that by this systematic interaction and information processing, it will help us to achieve unbiased, informed decisions beyond our personal knowledge limitation. So that's the first direction. The second direction, it's about the communication bandwidth and efficiency. because I realized that to express our idea to others or to interact with your works, it's inevitable. You have to encode your idea into language, into words or actions, and they are quite limited expressions with losses in transition, just like what we're currently doing. However, we can certainly benefit from the machine learning and use it to decode extra signals or information that we carry to reinforce the communication. And one really intuitive and additional signal we can use is our brainwave, as it directly reflects the activity of our thoughts and our minds. And what I did is I investigated current existing EEG decoding neural networks and proposed and improved the structure based on prior knowledge. Actually, it's level 2 from last chapter, the methodology-wise. And I proved that this new structure can achieve quite advanced in the imaginary task of event classification. So it actually works. It can help us to do classification. And during this investigation, I realized that the original signal certainly contains more information than the given label, just like this slide. And this provides us a whole new opportunities to express our personal preference, our feelings, and subconscious perceptions without any traditional formalization methods. So in other words, it can read your mind and then reflect on the work. So yeah, that's the whole major part. If there's one word to summarize this dissertation and all of my 4 years Ph.D. works, that would be alignment. I came to Germany since 10 years, 1/3 of my life so far. And it's been really important part of my life. And I found that in German there is a word that Gedankengang, means the thought path, of course, can perfectly describe my effort. All I'm trying to do is to make sure that AI development from the fundamental level can really align with our Gedankengang. We have to understand it and make it understand us to make sure that the technology undermines our human capabilities and autonomies. What we can do further? First, we can explore more fundamental elements of intelligence. In this paper, in this dissertation, I only I narrow it down to causality, one factors that we understand or perceive the world. But there's certainly more elements or mechanisms make us intelligent, such as scaling, recursion, emergence, or another such as energy-based model or entropy reduction. Such mechanisms are really interesting and worth further explore to make the AI more like us, intelligent. The second, alignment beyond the knowledge. Because in this dissertation, I primarily focus on the engineering, scientific discovery and design domain. So the information carries in our knowledge is primary. And that's more easy compared to another factors to embed into the machine learning model because you can write it explicitly. But to make AI to align with other factors, such as ethical standards, moral principles, and social impacts, and so on, they are really important, but it's more implicit. So I doubt that the way we encode our knowledge would work on these factors. However, I think the decision-making process alignment and communication alignments could be a really good start point to do so. The third one is integration with neuroscience and cognitive science. We already got a lot of inspiration from these two domains to develop our AI, and there is certainly more mechanisms we can use to benefit from, such as spiking neural networks or some mechanisms to help us against the catastrophic forgetting that the current AI are suffering from. So that's a really broad and wide open domains we can go for. And finally, it's top-down encoding with large models. Because when I started this topic 4 years ago, there is no large language models and so on. So I still carry this engineer and deconstruction approach to see what's the fundamental elements of our intelligence or our decision-making process and try to encode it or hand-code it into the machine learning, especially in its mechanisms. So it's kind of like a bottom-up approaches. However, with this new large language model emerging, it's less likely we can still fine-tune its organizations and do the exactly same thing. But there is another way, we call it the representation engineering. It actually uses the natural language to integrating complex knowledges such as law or like social communities, agreements and stuff into the large language model to make the model understand the world. So I can see that there is two approaches we can do. One's bottom up to make it more like us intelligence, and one's top down to make it faster, comprehend, and understand the words we process. And I can foresee that these 2 points will merge, will meet somewhere in the middle point. And I'm really looking forward to see how it would go. So yeah, that's it. So to finalize this presentation, I'll propose one final question and answer with my own word. What would be the purpose of designing such an assistance, machine assistance? It would be to know you and to know us. And here you will see all the included publication for this dissertation. And finally, is acknowledgement. I truly thanks for all of my friends, my colleagues, my girlfriend, and all professors and my parents to help me go through until this stage. Thank you very much.
Yeah, thank you very much.